In this section, we're going to learn about how magnetic fields can create currents. Now, we learned about the source of magnetic fields, which is in currents, so currents create magnetic fields. But there's also the reciprocal relationship, which is that a magnetic field, which is changing in a certain way, can produce a current. Before we can start, we need to go over some definitions and review one topic. Now, the things we're going to define are the area vector. A planar area can be represented as a vector which is perpendicular to the area, and the magnitude is equal to the area. We're also going to define something called magnetic flux. Now, the magnetic flux measures the amount of the magnetic field vector which passes through an area, and you'll see what this means, passes through, in a little more detail when we discuss this. Finally, I want to review something which should follow from what we learned about how currents create magnetic fields, that a closed loop of current will create a magnetic field, and we can use a right-hand rule to determine the direction of that magnetic field inside the loop. As I said before, the area vector is a vector which is perpendicular to an area, and the magnitude is equal to the area of that surface. Okay, so this is a definition which is only valid for planar areas, areas which are in one single plane, because then the direction of the area vector uniquely defines the orientation of that plane. So, for example, if you had a circular area, we could define an area vector on the inside of it, which in this case is coming out of the plane. And if that had a diameter d, the magnitude of that area vector would be pi times d over 2 quantity squared, or pi quarters d squared. Or another example would be a square area, let's say, that's in on a coordinate system. Let's imagine, say, that there's a square area which is in the YZ plane. Now I could choose an area vector here perpendicular to it. If the side of this, let's say, is d, then this area vector would be d squared times x hat. It would be a vector in the x hat direction, which is perpendicular to the YZ plane, and has a magnitude equal to d squared. Note also, we could just as easily have picked a vector in the opposite direction. Note, in this case, the vector A is minus d squared x hat. It has the same magnitude d squared as the other vector, it just happens to point in the opposite direction. Now, this is a freedom that you have in defining area vectors, as you'll see in solving problems involving magnetic induction. You have to define an area vector, and there are two choices, and as long as you're consistent with the direction you choose, then your result will be correct. Okay, to motivate the definition of magnetic flux, let's consider a square area here that is inside a region with a constant magnetic field. So I'm going to draw some field lines here representing that magnetic field. And let's have it so that the magnetic field is perpendicular to the area. Now, in that case, the magnetic flux, if we define the area vector to be in the direction of the magnetic field, the magnetic flux will just be the area times B. So it's just the, and this measures the quantity of magnetic field going through the area, because, if you increase the magnetic field, if you doubled it, let's say, then the flux would double. Likewise, if you double the area, even though the magnetic field is the same, the flux doubles because you're doubling the area, so there's more magnetic field going through that area. Imagine now a situation where you had again the area vector in the same direction, but imagine the magnetic field now is in the opposite direction. Now in some sense, this uniform magnetic field now is going the opposite way. It's not coming through in the same direction as the area vector, it's going through the opposite. And to distinguish that from the previous case, we would say that this is negative, because the area vector and the magnetic field are in opposite directions. So in some sense that magnetic field is going the wrong way through the field, through the area. But notice the magnitude of the flux is the same. Okay, so if you believe that, let's try another case in which we have our same area vector, our same area, but now imagine that the magnetic field is perpendicular to the area. In that case, none of the magnetic field lines pass through the surface. They don't pierce it or pass through. They're all parallel. In this case, we would expect that the flux would be 0. Now you can look at our previous results where you have the magnetic field vector parallel in the direction of A, you get a positive number, parallel in the opposite direction, or 180 degrees away from the A vector, you get a negative answer of the same magnitude, or when it's perpendicular, you get 0. Now this should remind you of a mathematical operation, which is the dot product or the inner product. So we define the magnetic flux as A dot B, and because this is a commutative operation, we can write it B dot A also. So I can draw these vectors in general here without loss of any sort of generality here as A and B with an angle theta. And I haven't drawn the area vector here. You can also show with this, I'll leave it as an exercise for the student to show that if you were to choose the area vector in the opposite direction, of course you would get this angle, theta prime. But cosine theta prime equals negative cosine theta. Therefore, the flux would only change sign, but not magnitude in this case. Okay, the last preliminary here is a review of B fields produced by currents. If you remember that a current on a wire, let's say if it's moving in the vertical direction, would produce a magnetic field, and you can use the right-hand rule to determine the direction. So if we put our thumb along the direction of the current, our fingers curl in indicating the direction of the magnetic field. It points, for example, to this side and this side. So what we find is that over here the magnetic field comes out. On this side the magnetic field would go into the board. Now, if you think about another current in this direction, then, and use your right-hand rule, you will also find that below this wire you would produce a magnetic field that goes into the board, and on the outside one that comes out of the board. Likewise, if we were to apply that rule here, we would find that it produces a magnetic field on the interior here, in this direction, on the exterior that way. And if we complete the loop and consider a short segment of wire here, again we find that it produces a magnetic field into the board on the inside and out of the board on the outside. Now if you take your fingers of your right hand and you curl them in the direction, or put your hand in such a way that they curl in the direction of this current, you'll find that your thumb points into the board, which is the direction of the magnetic field inside. And that is the general rule for determining the direction. So for example, if we were to have a circular loop of current, and there was a current produced going in the counterclockwise direction, we would know that inside this current loop there's a magnetic field coming out of the board, and outside the magnetic field actually goes in the opposite direction. Again, if I know this because if I curl my fingers of my right hand in this direction, my thumb is pointing up. if we were to look at this loop on the side, so imagine viewing this from this side direction here. We're looking this way. This is supposed to represent an eyeball in profile. So we would see this right here. The magnetic field lines then would appear like this. And you can see, sure enough, they come through the loop to the left, but then they close back around and come back in from the right, moving towards the left. So that outside here, the magnetic field lines are moving to the right, down here to the right, but inside they're moving to the left, which is the direction indicated by this right-hand rule. So the right-hand rule here is that if we curl our fingers around in the direction of the current around our loop, the thumb will indicate the direction of the field created by that current inside the loop. We're now finally in a position to state Lenz's law. Lenz's law says that when the external magnetic flux through a closed loop changes, a current is induced in the loop so that the internal magnetic flux, that is the flux created by the loop current, opposes the change in the external flux through the loop. Now, to try to clarify this external magnetic flux, this is created by some externally imposed field. So the idea is you have a loop of wire, for example. It's in a magnetic field. That magnetic field is created by other magnets or other currents far away that may or may not change, but they are not produced in any way by this loop of wire that we have. Now something's going to change. Something will change so that it changes the flux through that loop. And we'll talk about the different ways this can change. But when the flux of that loop changes, there's a current produced in that loop of wire. That current loop in that wire itself produces a magnetic field. We'll call that the internally produced magnetic field, which creates its own flux inside the loop. That will create either a positive or negative flux. All right, that's by this induced current will create its own magnetic field. That flux is going to oppose the change in the external flux. So for example, if the external flux reduces and is positive and its change is negative, the internally produced current will produce an internal flux which will be positive, so that the net change in flux is minimized. Let's take an example to see how this works. Imagine a situation where we have a loop of wire here that's in the horizontal plane, and we have a magnet underneath it with a north pole and a south pole. And we hold it close to the wire, and then we move it very rapidly away, so in 1 second it's moved down to this farther distance. Now the question is, in what direction will the current be induced in this loop? Will it flow in this direction so that it's counterclockwise when viewed from above, or will it flow in the opposite direction so that it's clockwise when viewed from above? So let me give you an example. Let me show you how we can think about this. First, we have to define an area vector, and what I always do is I think about the direction of the magnetic field initially. So initially, this magnetic fields are pointing away from a north pole, like this. So the initial magnetic field, there's the B field, points in the upward direction. I always define my area vector in the same direction as the initial magnetic field. It is a convention, and you can define it however you want, but I point my area vector in the same direction of the magnetic field. So if I were to draw, let's say, a graph of the flux here versus time, and flux is not a vector quantity, it's a scalar quantity, so but it can have positive or negative values. But initially, if you look at this, the A vector is in the same direction as the B vector, so it's going to have a positive quantity. So I'm going to represent it by this arrow. Now remember, it's not a vector, I'm just using this arrow to represent that it's a positive. If I read over here, I get a positive number. Okay, So that's my vector representing the initial flux. Now we want to think about the final flux. Now the magnetic field around this magnet will be the same, but you'll see as it gets pulled away, fewer field lines pass through this loop, the area inside the loop, and so we expect the flux to decrease. And in fact, as you get farther away from a magnet, the magnetic field will decrease, and although the area vector is the same here, the magnetic field is weaker, but it's still positive. These are still in the same direction, so we would expect a positive vector, which is what I've drawn here. Now then, we have to look at the change. The change in the flux will be what we have to add to the first vector to get the second vector. Now the first vector is at this level, and the second vector is at this level. This is phi initial, this is phi final, or at time 1. The change in flux, of course, must be a negative number to get the flux to go from its initial positive value to a smaller positive value, right? So the flux is negative. Since the flux is negative, we must have the change in flux is negative. We must produce a current which creates a magnetic field inside the loop, which creates a positive flux. Okay? So think about a magnetic field inside the loop in this region, which create a positive flux. To create a positive flux, it must point in the direction of A. So if we can create a magnetic field inside the loop which points in the direction of A, we will create a positive flux which counters this negative flux. Now if you use the right-hand rule, you'll see that if you put your thumb in the upward direction, your fingers will curl in this direction around the loop, that is, in a counterclockwise direction when viewed from above. Okay? So that implies, so let's repeat, implies, since delta phi is less than 0, the induced magnetic field must be positive. Therefore, the induced must be parallel the A vector or up. That implies that the induced current is counterclockwise viewed from above. Okay, so let's see if you can follow the reasoning on this problem. Imagine now you have a loop of current like shown, and you have an ammeter here which measures the current through this loop. You move the north end of a magnet towards the loop. What is the direction of the induced current viewed from the meter side? Viewed from this side looking this way, do you see current flowing clockwise or counterclockwise? Try to see if you can answer that now. You can stop the video and try to answer that. Now here's a hint if you're having trouble. First, you can think about defining an area vector. Now think about what I said. One simple way is to define the area vector in the same direction as the magnetic field initially, and then think about the sign of the flux. And think what will happen to the sign of the flux. Will it decrease, or what will happen to the flux? Will it decrease? Will there be a negative change, or will there be a positive change? You can try, see if that helps you. If you're still having trouble, try drawing a graph again of the flux over time, and initially the flux is positive. Now as you move it towards the loop, what will happen? Well, the magnetic field of course will increase. So you'll get a larger flux. Now if you think about it then, the change in flux then is positive. Okay? So now see if you can answer the question from here. Now if you're still having trouble, I can help you out more. because this change in flux is positive, we want to produce a negative flux. The A vector is coming out. For a negative flux, the B vector must be going in, the induced B vector. Now, using your right-hand rule, if you put your thumb in the inward direction here, what you'll find is that your fingers curl around in the clockwise direction, indicating that the current must be induced in a clockwise direction. Here's another one you can try out. Immediately after you close the switch, it's talking about this switch over here, what will the direction of the induced current, again, what will be the direction of the induced current, again viewed from the meter side? Now, if you can't see this clearly, this battery is oriented with the positive side on this side and the negative side on that side. If you're having trouble, here's a hint. Think about the direction of the current that flows through this first loop when you close the switch, right? When you close this switch, you'll connect it here, and then you'll see, since this is the positive side, you'll get a current going through here, and the current through here will be in this direction, which is the clockwise direction when viewed from this side, right? So see if that helps you. Here's another hint. As this current is produced, it produces a magnetic field through the center of this loop, which is directed like that. That's the external magnetic field that's created by this loop, or this loop creates a field. Now, since this loop here is so close, it will also experience a magnetic field on the inside pointing to the right. Think of that as the external field that's imposed on this loop. And what happens when you close the switch? See if that helps you. Okay, so let's give you some more hints here to help you along, and stop this anytime if you think you can answer the question. What I'm going to do is define an area vector, and the area vector here, since initially the magnetic field is 0, I'm going to define the area vector in the same direction as the magnetic field finally. So if I were to draw this plot now of the flux, again this is the flux through the second loop, not the first loop. At the initial position, the flux is actually 0 because the loop is off, right? I mean, the current is off. But finally, the flux has some positive value. So this is the final flux, and here's the initial flux. And you can see, of course, that the change in flux is positive here. And in fact, equal in magnitude to phi1. Now see, okay, so that will give us the question now, because since the change in flux is positive, we want an induced flux that's negative, because this is positive, that's the external flux change. We want an induced flux which is negative, which means we want a B field, an induced B field, which is opposite our area vector. That, if I stick my thumb along this, I find that the current that I get is in the opposite direction, which is counterclockwise, which is the correct answer.